Hello, I'm Mohamad Shahdloo, and I'm going to give you an introduction of balanced SSFP sequence and its properties. There are many different pulse sequences designed to achieve various goals, but in general, we may group them into spoiled and non-spoiled. In spoiled ones, like many conventional gradient echo pulses, the transverse magnetization becomes zero in each before each RF comes. This can be achieved in two ways. Either a TR is a selected line, which leads to the transverse magnetization to die out before next RF, or they may use crusher gradients to kill it manually. In these sequences, the steady state refers to the steady state value of the longitudinal magnetizations only. But if the crusher is not used, the residual transverse component play a role in the effect of the next RF pulse. In fact, if the TR becomes short enough, tails of the FID signals and spin echo signals overlap, which produce a steady state signal in the transverse plane. We call this steady state in the transverse plane SSFP signal, steady state free precession signal. This sequence has some benefits and some limitations. Because of the nature of creating transverse steady state, the TR should be short. This means that the imaging time is much faster. However, as we will discuss later, this sequence has the highest SNR compared to other present sequences, and due to these facts, it can be used for cardiac, which needs high-speed imaging, and angiography, which needs high SNR. There are two more important limitations. The most important one is that SSFP is sensitive to off-resonance frequencies. This sometimes creates banding artifacts across image, which should be taken care by further processing or our techniques like multiple image combinations. The other problem is the dropout in areas which have a sharp change in susceptibility and magnetic properties. This also can be carried out using further corrections after the imaging in the post-processing step. This figure is a representative timing to produce bSSFP signal. The term balanced in the bSSFP signal means that all gradients are refocused in each TR cycle, meaning that the area under each of them in one period of TR is zero, as you can see in the figure. The second thing to note is that flip angle of the consecutive RF pulses should increment by constant value. We usually use 180 degree increment in the RF flip angle because it usually gives the most signal. As you note, acquisitions are performed midway TR. This is because in this sequence, TE is equal to half of TR. There are other namings in the industry for the sequence, such as refocused SSFP, Fiesta, balanced FEE, and true FISP, which multiple manufacturers use each of them. Here we are showing movie of the time course of the change in magnetization across the SSFP sequence. As you see, magnetizations are refocused midway each TR, and each RF introduces a 180-degree flip. Let me play that. You see that signals are flipped, refocused, flipped again, refocused again, and this continues forever. Okay, this is a balanced SSFP signal profile in one period, in which you can see very flat passband, but also stop band in some upper resonances. These stop bands will create a banding artifact. Also note that the phase in the passband is very good, flat, as you note, which are good properties for a sequence. On the left figure, you see a timing diagram of the two TR cycles. You see that again all gradients sum up to 0 in each TR. This means that in the K space we start from the origin, and by decreasing Gx and increasing Gy, we go first to the left and up, indicated by the red point T1. Then Gx starts to accumulate and we move to the right in K space to the point T2. Then resetting Gy and Gx gradients, we return to the origin again. In the next TR does the same movement, but the difference is that because of the 180-degree RF pulse, we probe the lower path of the K space instead of the higher path. This way, by changing the magnitude of the phasing gradient, we may probe all of the K space using this timing. It should be noted that many other combinations of gradients can be used to probe the K space, but the important point is that they all should start from the origin and also end in the origin, and the signals should be refocused in each TR. This figure shows a relationship between balanced SSFP signal and some parameters. We may derive a closed form solution for a signal in SSFP. From the relationship, it is seen that signal depends on the flip angle and on the ratio of T1 over T2. What we can see in the plot is that for different T ratios of T1 and T2 and alpha, the signal is different. An important point on the plot is the curve for T1 equals to T2, the green one. This curve reaches approximately 0.5, which means that 50% of the magnetization is we get back from the magnetization as a signal. This T1 equals to T2 is somehow true for some tissues like fat. This means that for fat we have very high signal and there's no other known sequence which reaches 50% of the magnetization as a signal. However, the signal for water is more closely resembled using the blue curve, because T1 and T2 for water obey that relationship almost. And optimal alpha for water is somewhere around 30 degrees. As mentioned earlier, there is previously proposed that we can combine multiple SSFP images with shifted passbands to get rid of the banding artifacts. This method can be used also to suppress fat and water in images. This, in some sense, is an extension to the two-point Dixon methods. In this method, an image and its passband shifted pair are added, weighted by their amplitude to the power of p, and then the sum is raised to the power of 1 over 1 plus p, which cancels the amplitude change which was introduced by the weighting in the summation. This method for p-values larger than 2, has shown to be able to remove banding artifacts very successfully, but it also is shown that with p-values between 0 and -1, we can use it for fat-water separation. Here we add and subtract signals and its shifted version to gain fat and water signals using the p-norm combination. As it is seen in the figure, we have a voxel consisting of 30% water and 70% fat on the left image, and 70% water and 30% fat in the right image. Yellow and purple curves are the signals for fat and water respectively. After using the p-norm combination with p equals to -0.8, we get the blue curve for fat and orange curve for water. It shows very good result in suppressing water in the image. Fat signal is somehow very close to the actual fat signal, and the water signal is suppressed completely. The right figure shows the opposite. Here fat is suppressed and reconstructed image consists of only water signal. This analysis, these curves are the results of the analysis just like the previous slide, but with a different p-value. Here p is -0.4. It is seen that we again have some part of fat-water separation, but this change in p-value has changed the performance of the fat-water separation. Thank you very much. I hope I could give some brief introduction into balanced SSFP sequence and some of its usages in the MRI field. Thank you very much for your time.